Welcome back to the next lecture on drone systems and control. Here we will see the Matlab demonstration of extended Kalman filter. So, we have seen in the previous lecture and tutorial that extended Kalman filter is very much similar to Kalman filter, but what is different? It handles the nonlinear systems, and to incorporate the nonlinearity in the algorithm, what we have to do is having Jacobian of the nonlinear equations, right. So, in extended Kalman filter, the things are like this. We have nonlinear state equation. Previously, when it's a linear system, we have the system as x dot equal to ax plus bu, and the output z is equal to hx. Then yes, of course, the process noise and measurement noise should be there, which can be there also, the process noise and measurement noise. So, this is a nonlinear state equation, x dot equal to f x u. What is x? X is the system state. What is u? U is the input or control input used to make the system functional. Then nonlinear measurement equation is z equal to h x u, the similar definition of x and u. We have to in order to incorporate this nonlinearity in the system, we have to take Jacobian by Taylor series expansion. So, the Jacobian of f, the function f, which is there in the state equation, is taken like this. It is a partial derivative of the function f with respect to x, and we get matrix fk. Then we have to take the Jacobian of h with respect to the state, that means del h del x, the partial derivative of the function h with respect to x. We have to specify the process and measurement noise covariances q and r. So, the importance of good modeling and tuning we cannot ignore into the system, because we have seen in the last lecture 9a that in lecture 9 itself, that tuning of Kalman filter, tuning of gains, tuning of the covariance matrices are very important to get proper or desired performance, right. Okay. So, extended Kalman filter goes like this. This is a prediction step, the first step, and the second one is the correction step. So, in prediction step, we compute the predicted values of x and p, that means state and covariance, at time at time k, given the quantities or parameters at time k minus 1, that means the previous instant. Q is the process noise, u is the control input at time k, right. Now, when it comes to the correction step, first we calculate the innovation vector, then which is yk minus hx hat k minus 1. Then we just derive the Kalman gain. Then once we get the Kalman gain, we compute the predicted or estimated state x and covariance p at time k. Okay. So, these are the final output of the Kalman filter or extended Kalman filter. So, here you see that in this particular step we have the function f, right. This is the function f, and then what happens here, we have the measurement equation h here. So, when these steps come, that means computing the Kalman gain and computing the covariance with based on the previous state, we have to take the Jacobian and include in the algorithm. Okay, fine. So, the extended Kalman filter flow goes like this. We have x0 hat and p0, that means the initial estimation and initial covariance matrix. Then first we do the prediction step, then we get the Kalman gain. Once we get the Kalman gain, we include that in correction steps and improve the estimate and estimate of the state and covariance, right. So, in general we run the Kalman filter or EKF once per new sensor measurement arrives. The number of iterations is then dictated by the data availability, sampling rate, and application duration. Some event based triggering are also possible. When the output or measurement is arrived, that time we can take. So, the tuning can be very much event based triggering. Okay. So, what happens here is this is the entire flow, extended flow diagram of extended Kalman filter. Now when we go to the particular MATLAB demonstration, we will see it one by one that how things are done. Fine. So we will go through a problem where we will see how to estimate a 2D target states with angle and range measurements using tracking EKF. Okay. So this is a function or command. So in order to see this particular model, we have to see how to initialize the estimation model. So we have to assume that a target moves in 2D. It can be implemented in 3D as well with the coordinates in 3 dimensions, but this particular example is in 2D. So we assume a target moves in 2D with the following initial position and velocity, which is very important because otherwise you can't start the computation. The simulation lasts for 20 seconds with a sample time of 0.2 seconds. Okay. So we see here that we specify the sampling time as this dt equal to 0.2 seconds. Simulation time is 20, that is what we have specified, that the simulation will last for 20 seconds. Then what is the time span? With starting from time t equal to 0 with the final time t equal to 20, we sampled the entire interval like this. Okay. Then we initialize the state. We have 4 states in this particular problem, that is x position, then x velocity, then y position and y velocity, right. So we specify the initial values like this. Then we have to specify the initial covariance that we specify. So the first one is x hat 0, right. The second one is capital P 0. Then we have to specify the process noise, right. Okay. Now we assume that the measurements are the azimuth angle relative to the position, positive x direction, and the range from the origin to the target. Okay. So we have 2 elements in the output vector, that's why we have to specify the measurement noise matrix like this. Okay. These are the units. So we specify the measurement noise covariance matrix. Okay. So it is a diagonal matrix where the first element, that means element 1 row 1 column 1 is this particular value, and row 2 column 2, that means the second diagonal element is 1. Okay. So we have to pre-allocate variables in which we need to save the results. So for that, what we need is that we have to tell what is the number of steps, that means how long we should carry on the iteration of prediction and correction. Okay. So it is kind of specifying the number of iterations. Then we have to save the true states, and the first in that will be the true initial state. Then we have to save the estimated states in another vector, we are specifying it like this, and it is being like we are kind of pre-allocating the variables where after all the iterations over we will be saving the results. Okay. And this is the measurement. Okay. So measurement, we have 2 measurements as we have seen here. One is azimuth angle relative to the positive x direction, and another is the range from the origin to the target. Okay. Fine. So we have to obtain true states and measurements. So for that we will start the iterations. We have to propagate constant velocity model and generate the measurements with noise. So we have already specified the process noise covariance matrix and measurement noise covariance matrix. Then we start writing the code or start the iteration like this. So I equal to 2 to length t span, I equal to 1 is the initial state. So we start our computation from I equal to 2. Okay. Then we run the state equation. This is the state model. Since it is a nonlinear equation, we don't write it as ax, bu and so on, but it is the entire state equation fx comma u, and then the representation of the process noise w comes. Then the measurement equation, it comes from measurement model, it incorporates true states, okay, and then there is a representation of the measurement noise, okay, fine. Now we can plot the true trajectory and the estimates. How we can do that? We can whatever values we have stored in the vector true states and measurements, we can use those vectors to plot. You can go through some other tutorials on Matlab that how to plot different results. Those who are very familiar to Matlab, it might be very trivial for you, but those who are attending the course in a very advanced level of your undergraduation and are not familiar with Matlab codes, we suggest that you go through some online materials on Matlab, and then it will be very easy for you to follow, okay. And in this course there will be some live sessions also where you can get familiarized with writing the code on Matlab, okay. So if we see here, we see that this is the output, angle and range, that's what we are getting. When we write the code, we see this kind of results, but this is what we are plotting. Now extended Kalman filter has not come into the way, right? Whatever we have shown till now is just simulating the state equation and measurement equation and then checking the states and measurements, okay. Now what we introduce in this particular scenario is the extended Kalman filter. So we initialize the EKF like this. We have the initial state estimate. The true states were something like 31, 41, something like this, what we have mentioned earlier. If we can go back and show you once again. Yes, this was like 31, 41, x position velocity, y position velocity, right? Okay, so what we do here, we just show the true trajectory and then plot the angle and range, right? Now we need to implement extended Kalman filter. For that we have to estimate the initial state, and that is 35, 0, 40, 0, right? Now this is the filter that we are using with the command or the function tracking EKF, where we have the states, that means the initial state estimates, then state covariance, which is equal to the initial covariance, state transition function, then measurement function, and then finally what we write here is the estimated states, okay. So we run the extended Kalman filter and show the results. So how we do that? We have to, so in the particular state equation, sorry, in the particular command we have all the steps of prediction and correction imbibed. So you can directly use the particular function tracking EKF, okay. Now once we do this and we run the filter by recursively calling the predict and correct object functions. So we have to do it with predict, this is one function, then there another one is correct, this is another function. So first one will take care of the prediction step, the second one will take care of the correction step, right? After that you can plot the trajectories, okay. Okay, so if we see the true trajectory, it will be something like this. 1 minute. Yes, this is the true trajectory versus estimated trajectory. So you can see that the true trajectory is plotted as a red line, which was there earlier also. Then we have our initial state estimate and then estimated trajectory, okay. And we can see that though it's a non-linear system, it is working more or less fine with extended Kalman filter, and though there are some errors in the initial positions, like that starting from within 30 to 40 seconds or so, but after the 30 to 40 meters at this particular area, this particular position, but when it goes beyond and the time progresses, then we see that EKF more or less gives a very nice estimate of the trajectory, right? Fine. Now the functions which are being used here are state model to incorporate the state equation into the system, then measurement model. Okay, these are the functions which we have used to get the state equation and the measurement equation, right? Fine. Okay, so this is how we have to write the code for extended Kalman filter. Now we will see some other example, and based on that we will specify how extended Kalman filter can be implemented in some drone operation. Okay, so we go to the next code where the code is written for drone yaw estimation with both Kalman filter and extended Kalman filter. Okay, you see we have to specify the simulation parameters, that is the time step. We want to run the iterations for t equal to 10 seconds, then we have the number of steps, then we have the time from we divide it like this from 0 to t, how much time we are having, right? Now we have the constant yaw rate omega that we are specifying here. We have the true yaw which we pre-allocate like this. Then we have the equation yaw true k is equal to yaw true k minus 1 plus omega k minus 1 dt. Okay, so this is the ground truth about the drone system and control. Then we have noise definitions with q and r. Then we have process noise, we have measurement noise specified like this in terms of their covariance matrices, process noise covariance matrix and measurement noise matrix, right? What we are doing after that is we are getting the noisy measurement. Okay, so we this is a yaw angle and we take a sine of that, then add the measurement noise, so that is the true measurement what we are getting, right? Then we initialize the Kalman filter or pre-allocate, then the states are zeros like this, we pre-allocate in this way, then we have the predicted value of the initial estimation of the Kalman filter. Okay, so in this particular example what we are going to show is that we have both Kalman filter and extended Kalman filter, and we have a plant which is non-linear in its nature. Fine, we will see that which works better. In the lecture on extended Kalman filter, tutorial on extended Kalman filter, I have shown this particular example results where it was very clear that to estimate a nonlinear model or nonlinear system, Kalman filter was not doing very good, it was not doing great, but extended Kalman filter was sufficiently better than Kalman filter. And when we were checking the error performance, we have seen that extended Kalman filter works better than Kalman filter and minimizes the error, right? Okay, so in this particular code we are seeing that there are both the filters, Kalman filter and extended Kalman filter. We have the prediction step, then we have to update the covariance, right? We do it for both Kalman filter and extended Kalman filter, right? Okay, now we have to update the covariance, then we have the updation state, also we write it as correction step. So we do that, we calculate the Kalman filter gain, right? Then we do it the here we get the gain for extended Kalman filter, right? And so what we are doing is that first the prediction step by for both Kalman filter, so prediction for Kalman filter, then it is for extended Kalman filter, then we have the same thing for Kalman filter, extended Kalman filter, right. After that, when it comes to correction step, first we do it for Kalman filter, then we do it for nonlinear measurement. So, the here you see the linear measurement is z equal to the yaw angle psi psi plus v, but when we do it for extended Kalman filter, then we are actually doing it for nonlinear measurement. So, it is becoming sin psi plus v. Okay. Now, once we end extended Kalman filter and Kalman filter based updation or correction, then we go for plotting. Okay, fine. So, if we run this particular code, yes, you see this black line is the true yaw angle. The Kalman filter estimation initially is doing okay, but then it gradually degrades, it is not being able to estimate. But for this nonlinear model, when we get the extended Kalman filter, we see that it is doing much better than the Kalman filter. Okay. So, this is why we use, when it is a nonlinear model and we have the measurement as sin psi plus the measurement noise component, then we see that Kalman filter is not doing good, but extended Kalman filter is working much better than Kalman filter, right. Now, this is the error performance. We see that when we are doing true minus estimated, then we see that extended Kalman filter error is this. So, this is 0. So, extended Kalman filter error is much closer to 0, or we can say that the mean value of the extended Kalman filter is close to 0, but we see that for Kalman filter the error is gradually increasing with time. So, from the position, or from the yaw angle, not position, from the yaw angle, we can visibly see that how extended Kalman filter is doing good, and when we plot the error, then also it is visible that the extended Kalman filter has kind of zero mean error. I haven't plotted the checked the mean value, but you can see from the plot that it is very much around 0, but extended Kalman filter the error is much high, right. So, the estimation performance of Kalman filter is not that good as extended Kalman filter. So, EKF performance is much better than Kalman filter, and when it becomes a nonlinear system, then the students need to understand that Kalman filter might not be sufficient, then we have to write the code for extended Kalman filter. So, to summarize, what is extra in extended Kalman filter? The first thing is that the filter uses the exact nonlinear state update and measurement functions whenever possible. The state Jacobian replaces the state transition matrix. That means state transition matrix is what? X dot equal to Ax plus Bu and all, and the measurement Jacobian replaces the measurement matrix. Okay. So, in the last code which I have shown you as an example, we see that the same nonlinear model, we use both Kalman filter and extended Kalman filter. Visibly it is shown by the Matlab plots that extended Kalman filter is working much better. Okay. So, with this I will conclude this lecture and see you in the control lectures in the next module. Thank you.